Hello. Our lab in the upcoming lab session is enthalpy of a chemical reaction. What is enthalpy? We'll talk about that. It's essentially energy produced by a chemical reaction. We are familiar with reactions producing energy, the temperature going up or the temperature going down. You actually see both of them. How much energy is produced, how much energy is consumed by a chemical reaction. How do we do that? Well, let's think about it in this way. Energy, joules, kilojoules. Chemical reaction, balanced chemical reaction. Then we do what? Then we figure out how many moles, the amounts, moles of each reagent we have, so we can determine the limiting reagent, because that controls the product, that controls the amount of energy produced by a chemical reaction. And to do that, we gotta calculate the number of moles of each reagent and consider the stoichiometry. So that's what we're doing. So at the end of the day, we want to look at the reaction and say this reaction produces so many kilojoules per mole of the limiting reagent. Let me get into the slide mode here. All right, there we are. And then let me pick up a pen, pointer options, pen. All right. So the objectives are, first of all, be able to determine, given a chemical reaction and the reaction conditions, identify which is the limiting reagent, and then using the limiting reagent, determine the enthalpy of the reaction. In this case, we have chosen an acid-base reaction. So limiting reagent, totally consumed, you're familiar with that in class, and then the excess reagent is whatever is left over. In testing which is the limiting reagent, we actually test for the excess, because there isn't the limiting reagent there anymore present in the reaction chamber after the reaction, because as by definition it's totally consumed in the reaction. So where does the energy come from? Well, we kind of know this already. Take gasoline, a gallon of gasoline, there's energy in there, and I do something with this gallon of gasoline and it gives me energy. What is it? That's something that we do. Oh, of course, it's combustion, in this case reaction with oxygen, for example, in your engine, and that system gives off energy. But how does it really occur? Well, the idea is that gasoline, or whatever compound we're dealing with, has within it some internal energy contained in chemical bonds. So there is energy in chemical bonds. As we process from reactants to products, we change the chemical bonds, and so we might get a situation where the energy of the products, the chemical bonds of the products, is lower. And so where does the difference go? In this case, we observe that difference as heat, so that's the case here. And the other case here is where we have the reactants higher, and so we must input the energy in order to get it from low to high. Exothermic, endothermic. All right, just the terminology here. Delta E, change in energy. How about if I go here, change, and H, which is called the enthalpy. The enthalpy is actually a reaction that's performed under conditions of constant pressure. And so if you think of our atmosphere, it's not changing much in pressure, so we consider that as constant pressure. And so if we have a reaction exposed to the atmosphere, then what we're measuring is the enthalpy. All right, so how do we do this in this case? In this case, what we've chosen to do is to have the reactants in solution. And so they are dissolved in solution, the reaction occurs, the heat generated or consumed by reaction is actually shown in the reaction medium, in this case water. So whatever is happening to the water, then we'll use that to profile the reaction energetics. And so we've seen this equation before. Q is equal to Cm delta T. C is the specific heat capacity, and we've determined that in the lab a week or so ago. This is the mass, and delta T is the change in temperature. In this case, this will be, we'll take that to be the specific heat capacity of water. That is, the solution is the same as specific heat capacity of water. And for all practical purposes, this is a reasonable assumption. Moving right along. So let me draw a graph here. And this graph is one that we'll get from our data logger, temperature, degrees centigrade, time. If we have our reagents, just one reagent, in this case in solution, and then we add the other reagent, in this case the temperature will go up and then stabilize, and so T final is up here, T initial is here, and so we can calculate delta T as T final minus T initial. And then if we know the mass, then we can go back in the previous equation and be able to calculate the energy. So here's the reaction of interest that we're going to perform. Hydrochloric acid, sodium hydroxide, those reacting, and the energy being absorbed by the water. And so here's a simple example. If you have 5.2 grams of solution, here's the specific heat of the solution of water. If this is delta T, then the reaction as performed would have generated 49.7 joules as performed, because of course if we're reacting more stuff, maybe greater concentration or whatever it is, that will change and we'll get a different value. Just showing here the cancellation of units using dimensional analysis. So here's our setup. The data logger, small temperature sensor, don't use the big one, small one. And here's our reaction chambers. There's a little plastic thing that goes into the styrofoam. The styrofoam keeps the heat in. And here's our autopipetter for dispensing our reagents. Remember to use the autopipetters correctly. And so what we'll do is, first of all, we'll take one of these out of here, put a little of those stir bars, and weigh the combo. That is the plastic cup and the stir bar. We'll know the mass of that. Then we'll do the reaction and whatever it is. And then post-reaction, we'll weigh the mass of the entire system. And of course, the difference will be the mass of the solution that we can then use in the calculation. So the setup goes like this. If I go up here, I don't want to go back. Let's see if go back. Yeah, the temperature there must be set up such that we have 2 decimal places. So there's a procedure in the lab manual that allows you to reminds you, you've done it already a number of times, allows you to do that setup. Appropriate sensitivity for the temperature, that is 2 decimal places. So here's our runs. Run number 1, water. What's water doing there? 2 mils of 0.50 mole hydrochloric acid. I know that that's a reagent. And then that's the other. What's the water? Well, we want to keep the volume the same so that it becomes easy to make comparisons from one run to the other. So the volumes in this case, 5 milliliters, the density being 1, we expect roughly a mass pretty close to 5 grams. So perform that reaction, start with the water, put in the HCl, and put this one last. There's an asterisk there. The reason is we choose this is 1 mil, so we can deliver it in one shot with the auto pipette. As you know, our auto pipettes don't deliver more than 1 milliliter. There's an error here, and that is, if you look at this one, this asterisk should be here. The reason is, in this case, of course, this is a one-shot system. You'd have to do 2 shots in order to get that in there. Okay, given this system, what is a limiting reagent? And so I have you calculating these in pre-lab. What's a limiting reagent? Well, you've got to calculate the number of moles and consider the stoichiometry. The stoichiometry is 1-to-1, so if we calculate the number of moles, then we can figure out who is the limiting reagent. Sometimes they're just equal to each other, and so either one is. All right, moving right along. So how do I calculate that? Well, as you know, we can calculate moles by multiplying the molarity times the number of liters of solution. So you need to change this from milliliters to liters. You know what the concentrations are. You can calculate the number of moles, and from that determine the limiting reagent. All right, so when we test for this, we use litmus paper, and litmus paper should be able to tell us whether we have excess acid or excess base, and therefore be able to confirm or check our predictions about which one would be the limiting reagent. And so here are just steps given for the various things. Remember to put the others first, and the water and everything else, and put the reagent that's got an asterisk last. You start measuring before you add the last reagent, so you can establish a baseline and then be able to see a temperature increase. Beyond that, you go one run after the other, and then you should be able to perform this lab reasonably quickly. It's only 4 or 5 runs, and so the measurement time should be about 20 minutes. Wear your lab goggles, and safety is very important, and then be able to do the calculations and check with each other and make sure that the calculations make sense. Have a happy lab and a happy day. Bye-bye.